Okay, hello everybody. I hope that you are having a wonderful day so far. I'm just going to do a quick check on my sound and then we can get started. So give me one quick second. Alrighty, so it sounds like the sound is working. We're just going to get started in about a minute, but if you have any questions in the meantime that you want to put into the chat, feel free to drop them in there and we will address them. Today's lesson that we have planned is about quadratic graphing. Sorry, not quadratic graphing, trigonometric graphing, which, as I've mentioned a couple times, we've been building up to, and I wanted to wait until these last 3 weeks so that we could really dig into this. There's a lot of stuff to cover in this unit, and so it's very, very important that everybody really takes the time to kind of go piece by piece. So yeah. Okay. Alrighty. So in this unit, we take all of the concepts of trigonometry that we've been learning since grade 10, and I guess technically since like grade 9 and a little bit before, but the real kind of SOHCAHTOA concepts that we've been learning, and we start to apply them to the unit circle, and then we take that information and we learn about graphing. So one thing I want us to do before we start any graphing is just a quick refresher on how SOHCAHTOA applies to what we call these special triangles. And as if you've been on the live stream before, you've definitely heard me talk about these special triangles, these guys right here, and the fact that I highly recommend everybody takes the time to memorize these. You are going to need these again in grade 12. In grade 12, we don't learn with degrees anymore. We learn with something called radians, but that's okay. Having these in your head as concepts is very, very important. So while we're looking at these, I want us to quickly do an example of, an example of a cosine. So let's talk about cosine of 30 degrees, right? If we remember SOHCAHTOA, write that there. So if we recall SOHCAHTOA and what it means and how it works and all of that, we know that cosine is adjacent over hypotenuse. So if we're talking about 30 degrees, we know that cosine is going to be root 3 over 2. And we know that the sine of 30 degrees is going to be the opposite over the hypotenuse, which is 1 over 2. Now, keeping this in mind, I want to show you guys something else. I'm going to open up the unit circle here. Let me just minimize it a bit. Hopefully everyone can see that. And actually, I'm just going to focus on this first quadrant. So if we look over here in the first quadrant, we can see that 30 degrees, which is this line right here, has a cosine of root 3 over 2 and a sine of 1 over 2. Now, that's why I wanted to show this quickly before we get started with anything, because as I've mentioned many times before, I sound a bit like a broken record. Memorizing these special triangles means that you have essentially memorized the entire unit circle. Because as long as you understand that cosine is like the x value and sine is like the y value, and I always tell people it's alphabetical, so if that's an easy way to remember that. So here we've got, for example, x, y, and you know where x is positive and y is positive, then you can actually use this information at any part of the unit circle. So if you look at 30 degrees off of 180 on this side, which is going to be 150, the x value is negative and the y value is positive, because in this part of the unit circle, x is negative, and in this part of the unit circle, y is positive. Okay, So that's just a quick refresher. The real situation we're going to talk about today is graphing this information. And when we first learn this in class, typically teachers will provide you with like a long list and they'll say, okay, get all the cosine and sine values for all of these angles. I find that that can confuse some people. So what I really want to just have everyone understand is really what is going on. We're going to be graphing sine and cosine, and we're going to place it on a graph, and I'm going to show you guys it's going to be looking a little bit like a Cartesian plane. But when we do graph it, we're going to be graphing from 0 degrees all the way to 360. And this is what we're going to call one period in the graph. So let me just pull up a graph here. Oh, one of these bad boys. Hold on a sec. Oh. Okay, apparently doesn't want to do anything, but that's okay. We're going to be graphing, and I'm going to show you guys what I'm talking about. Let me just expand this quickly. We're going to be graphing the unit circle from 0 to 360 degrees for this initial piece. And what we're going to be graphing in particular are the sine and the cosine functions. So let me just erase that quickly. And I'm going to pull up the unit circle as well so that we can kind of take a look at how this all works. Okay. So as I've mentioned to you guys before, the trigonometry unit is one of the most useful units because it's going to come up for you over and over again. It's very much something that you need to master when you are in grade 11. It's not that you need to, like you can master it in grade 12. It's just that it'll help you a lot to master it in grade 11. So let's go ahead and talk about the two different main functions that we care about in grade 11 trigonometry graphing. The first is the function of x equals the sine of x, which we're going to draw in blue. And actually, no, I lied. I'm going to do the first one as f of x equals cosine of x, because it's actually just going to be easier. So on here, let's go ahead and map out our numbers that we care about. So I'm going to get a black pen here. Couple things I want to make really, really clear for you guys. When you're graphing a standard cosine or sine function, they should go from -1 to +1. So I'm going to call this -1. I'm going to call this +1. And then that's on the y-axis. On the x-axis, it should go from 0 to 360. Why is this the case? Well, if you think about it, on the y-axis, you can only go to 1. If you'll see what I mean in a second. Like, no matter what, no, there's a better way for me to say that. Basically, as you go through the different degrees, those are going to be your independent variables. The dependent variable is the answer to the sine or cos, which is going to be only from 0 to 1. And you'll see what I mean in a second. So again, remember that on the cosine and sine graph, you have cosine as the x value, sine as the y value, but that's on the unit circle I meant to say. On the graph, you have this going up until ideally 360 degrees. So I'm going to go ahead, put some little things here so everyone can see what I mean. Okay, so for example, we're going to want to go from 30, no, that's not going to be enough. So this is going to be 90, 180, 270, 360. Yeah, we're going to do it like this. 90, 1, 2, 3, 180, 1, 2, 3, 270, 1, 2, 3, and here we've got 360. Okay, the reason I'm showing this to you guys from 0 to 360 is because that is what we call one period of a graph in the trigonometric sense. One period just means the amount of time it takes the graph to get from where it started back to where it started. And I'll show you what I mean. Let's get the red pen here and let's start graphing the cosine of x. So let's look here. If we've got the cosine of 0 degrees is 1. So I'm going to put that right here. Next, I'm going to take a look at the cosine of 90 degrees, which we can see here is 0. So my y value is going to be 0. Because remember, the y value is the answer to the cosine of the angle, which is the x value. Okay, up next, we've got 180 degrees. That is -1 on the cosine. So we put that here. And we've got 270 degrees, which is going to be 0 again. And then back up to 360 here, which should be 1 again. And we're just going to connect this. Oh, that was a terrible line. It is so much harder to draw like this kind of graphing line. I can't even express to you. Sorry guys, I'm also a bit of a perfectionist, which can be annoying sometimes. Okay, we got this. We can do this. Oh my god. Also my graphic tablet pen is having a really weird day today. So I think the battery might be starting to go on it. And I need to fix change out the nib. Anyways, point of the story. Okay, this is a cosine graph. So one thing I want you guys to remember, cosine graphs always need to start at their maximum. So like right here, that's its max. This is its min. So a cosine graph always starts at its maximum. Let's take a look at the sine graph now. The sine graph always starts at the axis of symmetry, which in this case is going to be 0. So I'm going to show you guys. What is the sine of 0 degrees? Well, as we can see here, that's 0. The sine of 90 degrees is 1. Oh. The sine of 180 degrees is 0 again. Sine of 270 degrees is -1. And we're back to 0 at 360. So again, if we recall that a period is the amount of time it takes for a function to go from the point where it started back to that same point where it started, then both sine and cos, this is really important to remember guys, both cos of x and sine of x have a standard period of 360 degrees. So why is that important? And this question is something that we have to keep in mind all the time. The reason it's important is because we are going to be given all sorts of variations of these two graphs, and we have to be able to graph them. And when I say variations, what I really mean are transformations. And if you recall our standard transformation, situation, if you remember from graphing quadratics, you have a situation like this. You've got like a, and then x minus h squared plus k, our vertex form, right? And then sometimes in here you'll have something else, like another value. And some teachers write this as a plus k. Oh. This is something where every teacher writes it differently. I just want you guys to remember that there is kind of like a standard formula. But in general, most teachers will write, that's a k, x minus d, and then plus c. Now, keeping all of this in mind, it's really, really important that we understand what everything what's going on with everything here. So I'm going to delete this, or erase this, I guess, and I'm going to tell you what the standard transformation formula for quadratic graphs is. So if we know that we have f of x equals, we have different variables. So I have a, and then, oh, we'll just do black as the standard. And then in here, you have sine, and then we've got, oh, there we go, a sine, and then different letter, use a green there, k, bracket, x minus d plus c. Okay. I highly recommend you guys write this formula down. I'm going to write it all with one color as well, just to make it a little bit easier for you to see. So we've got f of x equals a sine k x minus d plus c. Okay, couple things I want to talk about. If you remember from when we were graphing quadratic transformations, the a term is the vertical stretch. That is the same thing here. So if these are our standard sine and cosine graphs, then the a term is what we call the amplitude. And another way of saying that is obviously the vertical stretch. And then if we have, if we recall back again to quadratic graphing, the k term that we see here is our horizontal stretch or compression. Both of these can also be compressions. But in our case, we're going to call this the period. Or what's it called? There's a word for it. Oh my gosh, now my brain is going to completely give up and not tell me what the word for that was. We'll just call this the horizontal stretch, that's fine. Basically, it tells us what the period is, but I'm going to show you guys the formula for that. Whoop. Okay, then the d here is going to be what we call our phase shift. Which means how far it goes right or left. And the c is our vertical shift. Okay, you guys. I know that that's a lot of information to take in. We are going to show you how this all works in a quick second. One thing that's very important to remember is understanding what the standard look of a cosine and sine graph is. Excuse me guys, sorry, my allergies are acting up again today. But essentially, as long as you know where the standard cosine and sine go, you will know what to do when you do your changes. There are a couple things I want us to really understand though. First and foremost, let me just actually remove this. Okay. So when we talk about shifts, right? Like let's say, for example, I wanted to create a sine graph that is, if I know my normal sine is f of x equals sine of x, let's say I want to create a sine graph that is, oh, let me get another color. Let's do orange. So let's say I said f of x equals sine plus, oh, sine of x, sorry. Sine of x plus, I'm going to make it minus 0.5. Okay, so that means everything in my sine graph is getting shifted downwards by 0.5, but the shape has stayed exactly the same because there's been no vertical stretch, there's been no horizontal stretch, nothing like that. So I'm going to show you guys how that's going to look. So if I go everything down by 0.5, that means that this is going to be lowered by 0.5, this is going to be lowered by 0.5. Where'd it go? Yep. 0. Yep, 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 and yep. Okay, so let's draw that out. Okay, not a perfect line drawer, but we all know that. So as you can see, it's the exact same shape as the blue, which is the normal sine graph, but it's been shifted downwards by a factor of 0.5. This is very important to recall as you're working on stuff. Now, let's say, for example, we do one where we've got, let's say, purple. Say I want to go f of x equals 2 sine x. So again, we're looking at our normal sine graph, which is the blue one. And let's see what happens here. So let me plug in my 2's there. Now, this just means that I am doubling the height. So if I usually start at 0, I'm going to start at 0 again. But if I'm moving over to my 90 degrees, that means I'm doubling the maximum. But all the time when it's supposed to be at 0, it stays at 0. Okay, so in this case, we have doubled our sine graph. So as you can see, it hasn't moved left or right. It still follows the exact same position that it was supposed to start in. Starts at 0, 0, but our maximum and minimum values have been changed. Okay, so if anyone has, I'm going to leave it like that for a second. If anyone has a question, let me know. Probably next week we're going to learn about shifting it, like flipping it, which is a negative, but that's down the line. I'm not going to confuse you guys today. Today we're going to try and just cover the main stuff. Okay. So now, this unit tends to be the unit where we get the most tutoring students because it really can be difficult to grasp when it's not explained properly. And even sometimes when it's explained properly, it just is not your standard math in the sense that, oh, why doesn't the cosine graph move? Oh, thanks, Allison. That's a good question. So the cosine graph can move. I'll show you an example. So let's do an example for the cosine graph. That's a really good idea. So let's use the fuchsia that I've got here. And if we've got f of x, so it didn't move because we specifically are talking about the sine graph in that function. But in this function, let's do cosine. So let's say I'm going to double the cosine function. And let's check out what that does. So again, it's just doubling my values on the y. So here we go, we have got 2. And remember that the cosine graph always starts at its highest point. And then this part is at 0. Here we're at 2. Here we're at 0 again. And here we're at 2. So this is like, again, if we just picture that this graph is made out of elastic bands. It's as if someone has just taken the elastic band and pulled it upwards and downwards by a factor of 2. And I'll show you what I'm talking about. So if we recall that the original cosine graph is the red one, and here I will actually make that a little bit wider so everyone can see. So that's actually a really good question that we got that Allison asked there, because it's not that the sine, like basically it's on a case by case basis is what I'm trying to say. So if this is the cosine graph, and we're going to do another example, so don't worry, like I know this looks like a hot mess right now, but if this is our cosine graph, you can see that the pink graph looks exactly the same. It's literally just stretched out. Okay? So it's not that the cosine graph and sine graph relate to each other. They're separate. It's like saying, it's kind of the same thing. It's not exactly the same thing, but like, let's say, for example, you have f of x equals x cubed, and you have f of x equals x squared. They're totally different situations. So same with cos and sine, they're totally different situations. I hope that makes a little bit more sense. I should have covered a cosine graph, and we totally will do some more examples. Let's just make sure. Okay. So what I want us to work on today are the strategies for both graphing these and also strategies for working backwards and graphing and creating a function from what the graph is showing us. So with that in mind, what we're going to do, so if everyone's okay, I'm just going to move away from this page, but if you want me to go back to it, that's perfectly fine. Just let me know. Now, let me grab the black marker, take it back to like 3 here. There we go. Okay. So hopefully that makes sense, Allison. If you have another question with regards to that, just let me know. But we're going to pull up another graph here. So the reason I think Allison's question is such a good question is because it's exactly why this is a confusing unit. Like, this is where we've always been taught that sine and cosine on the unit circle are kind of one thing, and then now all of a sudden we're being told, well, no, they're completely separate. And all that means in terms of their separateness is that we're just observing them in their own situation. So when we talk about cosine, we're only talking about how the value of cosine changes as you go to a different number. So if we look at the unit circle here, and I'm saying, okay, I'm at 30 degrees, cosine is root 3 over 2. At 45 degrees, cosine is root 2 over 2. At 60 degrees, cosine is 1 over 2. At 90 degrees, cosine is 0. So what I've often recommended to my tutoring students in the past has been, oh, these have now been connected to each other. And that does not come off separately. There we go. Okay, cool. The annoying thing about this is that I actually really only need the first quadrant, because the first quadrant tells us everything. You know, we'll just get rid of him for a second. Okay, so let's talk about graphing. What I highly recommend to you guys is to always have the unit circle in front of you as you're doing these, especially in the beginning, because it will give you a visual to look at. That's and visuals inherently are things to look at, but you know what I mean. Now the graph I just showed you, or the quote-unquote Cartesian plane I just showed you, obviously was not a normal Cartesian plane because it did not go into the negatives. Why is this red? This should be black. It did not go into the negatives. In actuality, cosine graphs and sine graphs continue on in perpetuity. They are infinite in the sense that they continue on and on and on and on, kind of forever and ever. So that's really important to remember. Whoops. That's really important to remember because it will come in handy a little bit later. For right now, I'm just going to use this like this so that we can kind of get an example. In the same way that values on the unit circle can go positive or negative, this can as well. But in general, for right now, we're going to start with examples where we're not moving too much, okay? Now, let us pull up our standard equation again. So again, our equation is going to be y equals a sine k bracket x minus d close parentheses plus c. Okay, so I'm just going to pull up the questions I want us to work on here. Sorry, over the few weeks that we have gathered a lot of paperwork, and so I'm just trying to find the exact question. Oh, there they are. Of course, I've moved them to the side and I'm searching in the wrong spot. Cool. So, you guys, it's very, very important that we teach this piece by piece. We don't rush because it will make a world of difference in the overall response. So I always like to make the one value like here, that's -1, and this is going to be 2, 3, 4-ish, 5, there we go. Okay, negative. I could have made this line a little bit longer, but such is life. That's okay. Okay, so as we recall, these are separate graphs. If we're talking about a sine graph, you will see the letters SIN. If you're talking about a cosine graph, you will see this. And we have to remember that they each have unique situations. A sine graph always starts at its axis of symmetry. And I'll give you guys a cool trick, I don't know. Oh, that's so annoying. Come on. Oh, that's not gonna happen. Pretend this says symmetry, you guys. There we go. So, a cool trick for you is actually that the C term, this guy right here, that is your axis of symmetry. For both sine and cosine. Okay? I'll show you what I mean. So let's say, for example, someone asks me to graph the graph y equals 3 sine x plus 1. Let's determine what each of these is. So this is the a term. This is obviously just the function. And the x. And this is the c term. I know that it's the c term and not any of these stuff in the parentheses because there are no parentheses. And that's really important to remember. So, keeping this in mind, let's go ahead and do this piece by piece, okay? But first I'm going to graph a normal sine graph. And then I promise we will do this for cos as well. I just find that sine is the easier one for people to learn first. So we're going to do that, and then we'll move to the next thing. So I'm also going to pull up our unit circle here and just move it to the side so that we can go based on this. Okay, so at the unit circle, if we've got, what am I trying to do, you guys? There we go. Okay, so if I'm trying to graph just the normal sine graph, I should also put my stuff in here. So this is 90, this is 180, this is 270. Is it 270? Yes, it should be. And this is 360. And then that can go onwards. Like basically we talk about a period of the graph. So we're going to learn just one period first, aka the amount of time it takes to get from its initial starting point back to that initial starting point, and you'll see what I mean in a second. So for the sine graph, a standard sine graph with no transformations, it looks like this: y equals sine of x. And if I look at my sine values here, the sine of 0 is 0. The sine of 90 degrees is 1. The sine of 180 is 0, which is on the other side of the unit circle. I just don't want to mess everything up here. The sine of 270, negative 1. And the sine of 360 is 0 again. So this is a full period of this function, meaning it started at 0 and it came back, like it went all through the function and it came back to its starting point. Because a lot of people would say, well, it gets to 0 at 180. It does technically get to 0 again at 180, but the point is that it didn't go through the full cycle, because these are cyclical functions. They keep happening over and over again. If this function was to go on, it would follow the same pattern in the next period. Okay? These are like waves. And a lot of things follow sinusoidal functions. We are going to learn about them next week in our word problem version of this. If we get to that, it might be the week after, we'll see. But okay, so this is our y equals sine of x. Now let's graph these changes that have occurred here. And let's graph them piece by piece. So let's start first with graphing just y equals 3 sine of x without graphing the plus 1. And this is one method that I teach some of the students who just were taught this by teachers who kind of brushed through everything, because then they get taught in a way that kind of teaches them everything at once, and then they're super confused. So we like to deconstruct it. Okay, so y equals 3 sine of x is just graphing the vertical stretch of this function. And all that means is that, again, we're multiplying the y values by 3. Because, again, it's vertical. So we start at 0, 0, because 0 times 3 is 0. At 90 degrees, instead of it being 1, it's going to be 3. At 180, it's going to be 0 again. Here we've got negative 3. And here we've got this. So as we can see, what I was saying earlier about the fact that the C term is the axis of symmetry. Oops. Sorry guys, I'm trying to draw lines that like don't look insane, just so that whoever's copying along can actually do so in a way that doesn't negatively affect their understanding. Okay, there we go. So as we can see, the C term in this case is still 0, so our line of symmetry is still 0. And our line of symmetry, as you can see, is actually the x-axis in this case. Okay? It goes straight through the middle of this function. Now let's say that we move up by 1. So now let's graph this function. This function. I'm going to graph it in this blue color. Is this blue or green? I don't know. So knowing that my C term is my middle point, and knowing that a sine function usually starts at its middle point, I can then go ahead and start at my middle point. Another way to think about this that's also easy is that you're just pushing the the y values up by 1. So here the y value was 0, now it's 1. Here the y value was 3, now it's going to be 4. And so on and so forth. So here the y value at 270 was negative 3, now it's going to be negative 2. And there we go. And again, we have one period of this function. Still following the same shape, because this is inherently a sine function in the sense that obviously it has sine in it. Okay? So I hope that makes sense. I'm going to show you guys a phase shift now. So I'll leave this up for a second, and then I'm going to actually delete the last one that I just, or no, I won't actually. It's fine. Or you know what, I will, because it does look confusing for some of us who like have never seen this before, it looks like a lot. So I'll show you guys what the next type of transformation will look like. All right. So just gonna get rid of those bad boys. So now let's do a phase shift. Let's say, let's do pink. It's this fuchsia-ish color. So let's say I'm trying to graph y equals sine x minus 90. Okay, so in order to do this, I actually need to keep on moving my numbers here. So let's add another little spike. 450, and then 540. Okay, so as we recall, the D term tells us the movement left or right. Now I'm going to show you guys something that's very important to remember. If the D term is here having a negative in front of it, then you move in the positive direction. If it's a positive, you move in the negative direction. And I will show you what I mean. So this graph says y equals sine bracket x minus 90. Because it's negative, we are going to shift the graph 90 degrees to the right. Meaning now that my new starting point is going to be at 90 degrees. And every single point on my sine graph is going to be 90 degrees shifted. So that's actually not that hard to do. All you have to do is just say to yourself, okay, well, if this was at 90 originally, then now it's at 180. And if this was at 180 originally, now it's at 270. And so on and so forth. So if this was at 270, now it's at 360, and onwards. And then here you've got your new function. And this is assuming that they've only asked us to draw one period of it. Okay? So from here to here, this is one period of this function. Okay? All right. I'm going to show you guys the k value, but not yet. We're going to go try everything with cosine next, and then later on we're going to talk about k, because I don't want to confuse anybody. If you guys have any questions about everything that I've done so far, feel free to drop them in the chat. Now, also I do want to mention, this is an overwhelming topic. If you're feeling overwhelmed right now, do not worry, that is normal. This is a lot to take in. It's a new concept completely in math. We're so used to using numbers, and even within trigonometry, we're so used to having like inputs and outputs and numbers, and this is a totally new situation. So don't worry if this is seeming complicated right now. This is totally one of those things that comes with practice. In fact, so I was teaching this these past couple weeks to the grade 12s because they have this same unit, except they do it in radians, like as you can see here. So for example, 30 degrees in degrees is pi by 6 radians. It's just a different way of expressing the same thing, basically. You guys don't need to worry about that, but point of the story is grade 12, you will do this again. That's why it's so important. And literally in teaching it to the grade 12s, I learned some new things about how to do this. So this is totally a practice. It takes time, and it's not it's not linear, no pun intended. But, you know, basically it's not something I expect everyone to understand completely by the end of this class. We're going to cover this for the next couple weeks. That's why I left this to last, because I really wanted to dig in and cover this properly. And if anyone has any questions at any point, or if even you think of questions after the fact, please feel free to email them to us. I will address them in the next week. So, okay, let us create a new page. Okay, so we've got this bad boy here. Let's put our lines in right quick. So we were just talking about sine functions. Now we're going to talk about cosine functions. And we're just going to have a merry old time. I'm also trying to speak louder. I know that some people have mentioned the audio doesn't come out like perfectly loudly enough. Just let me know, please, if it's coming out wonky for you. So now we're going to talk about cosine functions. Again, these are sinusoidal functions in the sense that they are repeating functions. They are cyclic functions, meaning they follow the same pattern all the way throughout. But they also follow their own rules. Just like how the sine function starts at its midpoint, the cosine function always starts at its maximum. And one thing we're going to talk about later, and I'm going to show you guys hopefully later, is if I don't forget. If I forget, just yell at me. Feel free to remind me. The sine and cosine function are basically just a shifted version of the same function. And I'll show you guys in a bit what I mean. Oh, 1 second. I'm getting a call from Beverly Hills, California. Gonna ignore that. Lord knows my long distance bill does not need that. Okay. Cinco. And again, I'm just gonna use my 90, 180, 270, 360. And remember how I was saying these can go negative? They totally can. This is negative 90. And this is negative 180. Because so far I've only been graphing one period of each function, but really, like I said, these functions go on forever. They actually have a domain of x is the, not equivalent. God, I always forget what this E stands for. If anyone knows it, just drop it in the comments, because I literally always forget what it stands for. But x is the whatever of all reals, meaning it goes on and on forever. The y, the range of a standard cosine function is y er, and then negative 1 is greater than, or y is greater than, or oh my god, I keep saying it wrong. You guys see what I'm saying here. It goes from negative 1 to 1 is what I'm trying to say. So a standard cosine function. Let's do that in red. Like I said, cosine starts at 1 because if you like, and if ever because obviously your teachers are not necessarily going to always let you have the unit circle in front of you. If you only have your calculator in front of you, all you have to do for this is just literally plug in cosine of 0 into your calculator. You get 1. Make sure your calculator is in degrees mode. So the way to do that is you press mode, keep pressing it until you see degrees, press that. That's really important because, like I was saying earlier, you know, in grade 12 you'll be worrying about radians instead of degrees. It's very important that your calculator is in degrees or you'll get the wrong answer. So next we're going to do cosine of 90 in our calculators, which we know is 0. Next we'll go cosine of 180, negative 1. So if you're following along and you have your calculator, I highly recommend doing this just so that you can get in the habit of it. Then cosine of 270, which is going to be 0. And cosine of 360, which we know is 1, because we know that that is when we return back to our starting point. Yay. Okay. This is, like I've said before, one period, aka cycle, of the function y equals cosine of x, aka the standard cosine function in which no transformations have occurred. So I'm gonna, and that's something that I really recommend just memorizing, that one period of the sine function or the cosine function in its standard format is always going to be 360. And the way to remember that is that the unit circle goes from 0 to 360. The E means belongs to. Thank you, Allison. Yes, I always forget, and I don't know why. Thank you for telling me that. That's actually, it makes me so mad that I forget it every time. It's like the one thing that's always on the tip of my tongue, and I don't ever remember it. So very good to know. God bless Allison. She just makes my day every Thursday. Okay, so you guys, let us go ahead and do some transformations to this cosine function. So let's practice with, oops, sorry, I was trying to test my color there. Okay, let's try something new. Let's, instead of having a whole number in the front, let's do a half. 1/2 of cosine x. And so remember that this a value, when we're talking about it in the format of y equals a cosine k x minus d, that's a d, plus c. So the a value is the vertical stretch, also known as the amplitude. And if those of you who are thinking about taking physics, you'll definitely learn about this in your waves unit. So we've got, because again, we know that cosine always starts at its maximum. The maximum was 1. Now it's being halved. It's at half. 0 is still going to stay at 0. Here we go. 0, half. And then when we pull this all together, oh my gosh. Again, I would say these are the one limitation of these silly pens. But I mean, as far as technology goes, they're pretty dope. So as you can see, this is literally half in terms of the height of the cosine function. Now, let's say we wanted to move the function in the negative. So remember, we're basing this off of the red one, okay? And I'm going to delete the purple actually just to make this easier, so I'll give you guys like 5 seconds to just copy that if you're writing it down. Okay, so now let's say we're going to go ahead and try y equals cosine of x minus, let's do 4. Okay, there's no brackets here. I know that that's the c term because of the fact that there's no brackets, and I just need to move everything down by 4. So if it was at 1, then it's going to go 1, 2, 3, 4. And in this case, it's very important to remember that this is actually our 0 because, like I've said before, the c term is another way of saying the axis of symmetry. So if the axis of symmetry used to be 0, then now it's literally just going to be -4. So keep on going. I don't know if I even have enough of these numbers here. This is -1, so this should be -5. This is a negative. Okay, so on and so forth. Yay! And I'm actually going to show you guys what I mean by axis of symmetry. So here, this is my new axis of symmetry. See that? So this is actually something that, like I said, I've been learning new things as I've been teaching this. This is something no teacher or professor in university ever like explicitly said to me. And it just clicked to me the other day, and I don't know how it took me so long, years of tutoring, I don't know. But it's just such a good thing to keep in mind. The C term is always your axis of symmetry, and it'll be very helpful. Okay, great. So I'm just going to remove that just because it's not something we would actually draw. Sometimes your teachers will draw it like as a dotted, oh God, there we go. Sometimes teachers will draw it as a dotted line. Sometimes they want you to draw your axis of symmetry. My dotted lines are always terrible, so I apologize. So again, this is one period of the function f of x or y, whatever you want to call it. F of x equals cosine of x minus 4. My frantic writing. Okay. So now let's talk about the k value. And the reason I've left it to last is because as I introduce the k value, I'm also going to teach you guys how to work backwards to create these functions. So let's erase all this stuff. Yay! Not what I was trying to do. There we go. Okay. So, erase, erase. Alrighty. In the k value changes the period of the function. And there actually is a formula for solving for the period of the function based on the k value. So let's say hypothetically your function is like y equals cosine 2x. So in this case, I know it's a k because it's in between the cosine and the x. It's not in the front. And this indicates to me that my k value is 2. So this is just the factor by which the period is being changed. And the formula for determining that is the period equals 360 degrees divided by k. Okay, so what I mean now by the fact that you can use the k value is that you're just going to substitute this value into this formula. So let's say the period of a normal cosine function is, not let's say, it always is 360. Well, now my new period for this function is 360 divided by 2, which is obviously 180. So that means my whole function has just been accordion smashed, as I like to say. And what that means is that everything is halved in terms of where it is on the x-axis. So I'm going to use this orange color to demonstrate this. So let's see what I mean here. Now, the starting point would still be at the same spot. Okay? Now, but other than that, I now know that I need to go from my first starting point, which in this case is going to be 1, back to where it needs to go by 180. One trick that I teach students who are first learning this is if you know that at the halfway point, usually, you are at its minimum value, well, now you've got your new minimum value halfway. And you know that your halfway point's like this. So this is now one period of the function y equals cos 2x. I hope that makes sense to you guys. Just like when we were graphing quadratics, that k value, which some teachers call a b value, it really doesn't matter. The letters, I have taken like pretty much every math course you can possibly take. Every teacher and every prof I've ever had has used different letters, except for A and C. Everybody uses A and C for the most part. In the middle part, everybody changes the letters. It doesn't matter. As long as you understand like the placement and what they mean, you'll be great. You'll be perfectly fine. So in this case, like I said, all the maxes and mins stay in the same spot. All that's happened is you have literally, like if anyone has seen those hydraulic press videos where you're literally just like crushing stuff, that's kind of what I picture is happening here. It's like a hydraulic press has taken this and just smushed it into a smaller period. Okay. So this can happen like for a number of reasons in real life. But again, let's not get into word problems today because it's just going to confuse everybody. So we're just going to focus on the fundamentals and then we will get to the next part. Okay, so let us now teach you how to work backwards. Okay, so I'm going to remove all this stuff. And when I say work backwards, what I really mean is if your teacher has given you a graph and said to you, give me the equation of this graph, you can do that, no problemo. And this is the part that most people struggle with, but I'm going to try to teach you guys as many tricks as humanly possible so that you never have to struggle with this, because it really is just about having a methodology. And a lot of times teachers expect us to kind of extrapolate the methodology on our own. I personally think that's silly. I think give people the tools to actually learn what they need. And then if they want to practice it, kudos to them. If not, you know, whatever. But I know that a lot of people get discouraged because teachers don't, and again, not all teachers, I'm not saying anything against teachers. There are some amazing teachers, but a lot of teachers that I have seen do not actually teach this way backwards. So if you have a teacher that does, kudos to you because that's awesome. Alrighty, I'm going to stop blabbering now and get to the point. There are some formulas I highly recommend you sear into your brain, and they apply for both sine and cos. So everything I'm about to teach you applies for both sine and cos. I just happen to have a cos value up on the screen. This is true for both, okay? So you can actually solve for all of these pieces in here very easily. Okay, so the a value, the k, the d, the c, they're all solvable. And I'm going to show you the equations for them. So the a can be solved by taking the max. So in this case, this is the max, because it's obviously the highest the y value goes in general. And you subtract the minimum from it, and you divide that by 2. Yay! The c value is very similar, and it's max plus min divided by 2. My number one tip is just memorize one of these really well, and then remember that the other one is the opposite. In general, in high school math, physics, chemistry, whatever, anytime I have an equation like this where it's like this or that, I've always told my students, like, literally just make sure that you only memorize one, because sometimes on a test you might get confused, and it's easier that way. Okay. So now I'm using the standard cos function just as my example. These values apply, these formulas apply for even when you have really, really crazy functions. And I'll show you what I mean in a bit. So, okay, and earlier we learned that the k value is equal to 360 divided by the period. And you can also solve for the k value because this is the same thing as saying the period equals 360 divided by k. I'm going to show you why that's the case real quick, just because every time I've ever shown a student this, they're like, wait, but what? What's going on? And it's just easier to explain it. So let's pretend that we are solving for, let's say we were given this formula, the k equals 360 over the period, and someone said, okay, but how do you isolate for the period? Well, you would multiply the period up, so you'd get k times period equals 360, and then you'd solve for the period by dividing off k from both sides. So that's going to cancel, and then you get the period equals 360 over k. So that's what I mean when I say they're the same thing. It's just a rearranged algebraic equation. Yay! Okay. So super valuable information here. Not valuable, but like super important information for us to remember, because this is actually the hard part in terms of solving for k sometimes, and you'll see why when we start actually doing it. I'll just rewrite that because my OCD is gonna go a little berserk if I don't. So yeah, because sometimes you'll have the k value, sometimes you'll have the period. It really just depends on whether you've been given the function or the graph, and you have to kind of work with whatever you've got. And then last but not least, the d value is very important. There's not really necessarily a standard function for, I mean a standard like equation I can give you, but I will teach you the trick on how to solve for the d value. So let's say for example, you've shifted this graph to the right by 90 degrees, right? That means it would look like the starting point is right here, and then everything is shifted, and it looks like that. Oh, that's too high up. Now, because so far we've only been graphing one period of each function, it's a little bit harder to describe. But let's pretend that this kind of goes on forever, and whatever, right? Now, I can describe this either as a sine function or a cos function, and I'll show you what I mean. So this purple function that I've just drawn, it can either be y equals sine of x, or it can also be described as y equals cos x minus 90. Why is that the case? The case is because if we look at it starting as a sine function, so right here, if it's a sine function, that means it starts at its midpoint and it just follows its standard sine situation. So because I'm claiming that it starts at its midpoint, and the midpoint is 0, 0, nothing is shifted. The midpoint's... Oh, your mic is going crazy. Oh, I'm sorry. Let me see if I can toggle. Is it a little bit better, Allison? Please let me know, because I don't want everyone to like have their ears going nuts because of me. Oh my god, it's 5 o'clock. Wow, we really just blew right through the time. So if you're here for the grade 12 class, this stuff all applies to you. So we're just going to wrap this up anyways, quickly. Not really. Dang it. Okay. Oh. I'm sorry, you guys. I don't know what's going on with my mic today. The grade 9 and 10s were also mentioning that something was wrong with it, and I've tried fixing it in the streaming software. I think I'm gonna have to get my brother to look at it a little bit more intensely. Better now? Okay. Hopefully it stays better. For grade 12s, if you're here for the grade 12 class, although I don't think anyone came new for the grade 12 class from what I can tell, this is stuff that applies to you guys too, so we're just going to wrap up this session and then we'll do your class materials. Okay, thank you for letting me know, Allison. I'm sorry that the mic was bugging like that. So okay, in case anyone missed what I was talking about earlier, it's really important to remember that sine and cosine functions, again, follow that same standard pattern. So a sine function or a cosine function is just a shifted version of each other. So like I said, this purple line can be described either as sine of x, because if we look at its starting point, it's at the midpoint here, or it can be cos x minus 90, because that's right here the cosine starting point, aka the maximum. So each of these functions has like a million ways, not a million ways, but quite a few ways that you can describe it. And it's just very important to remember. So the d, just one thing that I would tell you is basically look at where the function, I know that's not the right purple, but starts based on standard cos and sine rules and select your function. Okay, you guys, so we actually went 10 minutes over because I just got really into this and was not looking at the time. We will continue this next week. There's so much more to learn about this concept. We're going to actually learn next week how to create the functions based on the graphs, because a whole part of this unit is like teachers will give you graphs that have no function attached to them, basically, and essentially they'll make you create the material. What's it called? The oh my gosh, my brain. They'll make you find the formula for it. Okay, so anyways, thank you guys for joining. I'm sorry we went a little bit late today. I hope this was helpful for you. Like I said, we will continue this unit over the next few weeks because it is really the most monstrous unit for grade 11. And if you have any questions that come to mind in between now and then, feel free to send us an email and we will address it next week in the chat. But for now, we're going to switch over to the grade 12 class because I'm not sure if anyone new started or not, but either way, I know that some people watch them after the fact. So we do have to cover some grade 12 stuff as well. So thank you guys. I hope you're having an awesome day. I hope that you're safe and healthy and well. Say hi to your families for me if you know me, and have an awesome weekend. Okay, so I'm just going to switch over to the grade 12 stuff now. Which is sad because I actually really love this quadratics unit a lot. Not quadratics, I keep calling it quadratics. Thanks, Allison. Thank you so much for participating. I really appreciate your help. It's awesome and very much appreciated. Alrighty. So, if I do have any grade 12s here, welcome. Sorry for making you wait a little bit. I appreciate your patience. We are going to actually cover my least favorite grade 12 unit today, but that's okay because it's still important and we do have to cover it. It's the families of functions unit, or operations on functions, which is super important. Okay. So, what are we talking about when we say operations of functions? Well, there are quite a few things that this unit entails. So let me just, operations on functions. Yay. Okay. So basically what we're talking about, there are obviously various functions in the world, and one of the important things to remember is that we can actually add, subtract, multiply, and divide functions with one another. And that's what we're going to be discussing today. So if we have like f of x and we have g of x that are two functions. So for example, if f of x is x squared and g of x is just x plus 2, so this is actually a quadratic function, and this is a linear function, then there actually is a way to add these together. So you might see something like the rule actually, which is f of x plus g of x. And another way to say it is f plus g of x. So this is one formula. So this is a sum function. And then we also have difference functions. So if you have like f of x minus g of x, another way of saying that is f minus g, that's a minus of x. Woohoo! Okay. So let us try these out with some different functions. Okay. Now, it's also really important that you keep in mind that these matter in terms of which letter goes first. So I'll show you what I mean. So say we have f of x equals 4x plus 2 and g of x equals x minus, let's just do 3. Okay, so now let's say that your teacher asks you to write them out f plus g of x. One thing that's really important to remember is that you've got to put the f function first in this scenario. So it's going to look like this. 4x plus 2 plus x minus 3. So we're actually going back to our polynomials unit of grade 9 to remember our rules about how this all works. So we've got 4x plus 2 plus x minus 3. Then we bring together like terms, so I've got 5x minus 1. Yay! So now let's try something a little bit different. Let's try b, and we'll say g minus f. Yeah, g minus f of x. So that means I have to put the g function first. And like I said, because of the polynomial rules, this is going to vary, right? So x minus 3, and then we'll put in brackets minus 4x plus 2. And then I have to multiply this in, so let's go ahead and do that. So we get x minus 3 minus 4x minus 2. And we get negative 3x minus 5. So as you can see here, we had two linear functions and they remained linear in the end. Okay, so when two linear functions are brought together, whether it's through addition or subtraction, the result is always going to be a linear function. We are going to do some examples where we bring together different types. Actually, I'm going to show you right now. So let's say we've got f of x equals 4x squared plus 10x plus 7, and g of x is equal to, I don't know, let's say 2x minus, let's say 15. Okay, so let's say your teacher asks you again, like something like f plus g of x. These seem really simple, you guys, but they get much more complicated. So I want us to have a good understanding of the basics, and then we will move on to the more complex stuff. So again, the f values, the f function goes first, so I'm going to put that in there. 4x squared plus 10x plus 7, and then plus, and then in brackets, 2x minus 15, and then get rid of the brackets. And because this is a positive, this is a negative, that becomes negative. Let's bring together like terms. X squared does not have a like term, but my 10 and 2 go together, so that's 12x. And then 7 minus 15 is negative 8. So this is our function. And so when we have a quadratic function and a linear function, as you can see, when they're only being subtracted or added, they're going to stay quadratic. And it makes sense because you did not have anything to get rid of that x squared, right? And you'll see what I mean as we go down the line. Now let's try g minus f of x. So that's going to be 2x minus 15 minus 4x squared plus 10x plus 7. So let's go ahead and see what that affects, that's going to be a different answer, obviously. So that's going to be negative 4x squared. That's going to be negative 10x. And that's going to be negative 7. And that's going to give us, we want to put our we want to put them in order of decreasing, the word is escaping me, but basically you want to put the x squared first is what I'm trying to say. My brain is just done for the day at this point, but you guys get what I mean. So negative 15 minus 7 is going to be negative 22. So as you can see, we got two totally different answers. This was f plus g of x, and this is that. Okay. So, whoops, let's do a flip here. Now let's try another example. So let's say I was given f of x equals 3x squared plus 2x plus 1, and g of x equals x plus 1. So, and let's say that your teacher asks you for g of x minus f of x. Well, that's the same thing as saying g minus f of x. And in this case, that's the same thing as saying x plus 1 minus 3x squared plus 2x plus 1. And that's going to get us, oops, yay. And then we can just rearrange. And then that's going to be minus x. That's going to be 0. And as you can see, that's what we got. Yay. Okay. So moving forward, you can also graph these. Like, there's lots of different things you can do with all of these. We're not going to get into that because obviously you guys know how to graph functions by this point in grade 12. But let's go ahead and look at the next situation, which is when we divide and bring together by multiplying different functions. So let's take a look here. Alrighty, so we've got f times g of x, oops, which is the same thing as saying f of x times g of x, which is the same thing as saying fg of x. Okay, so let's say, for example, our function for f is the root 3x. And then g of x is square root x squared minus 4. So for a product function for this, if we had fg of x and it's going to be like this. Great. So you guys, basically, one thing to remember is that when you multiply radicals like this, you can actually multiply the radicand, I think it's what it's called, the stuff that's inside the radical basically, just together. Yay. Okay, so basically at this point we're going to get the square root of 3x cubed minus 12x. And this is where we get into the situation about domain and range that we will talk about hopefully next week. I'm getting a message that my sound is still messed up, you guys. I keep trying to fix it. I don't know what's going on and whether it's my internet or what. But if it's just going to be terrible sound, I think we might just leave this till next week, because I don't want you guys to miss out on this unit. It's actually like the final unit of this course. So I'm just going to wait to see if it sounds any better, but it doesn't seem like it is. Yeah, you guys, I don't know what's going on with this or why it's not working. It's very frustrating. So you know what? We're going to reconvene this unit next week. And if you guys have any questions, bring them next week. But yeah, I don't know. I can't seem to fix the sound. I don't know what's going on with it. So I'm going to let you guys wrap up early today. And we will hopefully make this up next week. Hopefully my internet and sound is working better at that point. I'm going to try and see if it's my microphone or what. I don't know. But anyways, either way, I appreciate you guys joining. I hope you have an awesome weekend. Stay safe, stay healthy out there. And just, you know, if you ever need someone to talk to, kidshelpphone.ca, they're awesome. And again, I apologize about this sound situation, but we're going to hopefully get it fixed for next week. Okay? Thank you, everyone. Have an awesome day, and we'll see you guys again next week, okay? Bye.